Let's start with a question that sounds super simple, but is actually, well, it's anything but. Is it possible for something to be completely 100% still? Turns out, the answer to that question is way more interesting than you might think. It really gets to the heart of how we describe the world around us. So, let's get into it.
Okay, so let me ask you. Right now, wherever you are you moving? I mean, you probably feel like you're sitting or standing perfectly still. But are you? For real? The answer, weirdly enough, is both yes and no.
Okay, picture this. You're on a bus. You're just sitting there scrolling on your phone. Now, compared to your seat, you're not moving an inch, right? You're at rest. But what if someone is standing on the sidewalk watching the bus go by? To them, you are definitely moving. You're zooming past along with the bus. So which is it? Are you moving or are you still? This is the big paradox. So what's the secret? It all comes down to one absolutely crucial idea, a reference point, or what a physicist would call an origin. See, motion isn't this absolute thing. It's always measured relative to something else. And agreeing on what that something else is, well, that's the key to everything we're about to talk about. All right, so if we want to talk about motion like physicists, we have to be super precise. Let's start with the basics. How do we even measure a trip from point A to point B? Turns out there are two totally different ways to do it, and they tell us very different things about the journey. First up, we've got distance. This is the one you know and love. It's the total ground you cover, every step, every turn, the whole scenic route. It's kind of like the number on your Fitbit at the end of the day. It just cares about how much ground you covered, the total number. In physics speak, we call that a scalar quantity. It just has a size or magnitude. And this butterfly is the perfect example. The distance it traveled is that entire squiggly red path, every little flutter, all the way from A to G. That's the full story of its trip. But then there's another way to look at it, displacement. Now, displacement is a little more direct. It doesn't care about the wandering path you took. It just asks two simple questions. Where'd you start and where'd you end? And then it draws the shortest possible straight line between those 2 points. And because it has a length and a direction, we call it a vector quantity. So let's go back to our butterfly. That long, winding red line was its distance. But its displacement? That's just the straight green line from A to G. It's the as the crow flies path. Now get this, if that butterfly flew around all day long and ended up right back where it started at point A, it could have a huge distance traveled, but its displacement would be 0. Wild, right? So, let's just quickly put it all together. Distance is a scalar. It's always a positive number, and it tracks the whole journey. Displacement, on the other hand, is a vector. It can be positive, negative, or even 0, and it's only interested in that straight line from start to finish. Understanding this difference is absolutely key. Okay, so we've got a handle on how to measure a journey. But you know what they say? A picture is worth 1,000 words. And for physicists, that picture is a graph. A simple graph can tell you the whole story of something's motion, all in one glance. Let's take a look. This right here is your classic distance-time graph. All it does is show how far something has gone, that's the vertical axis, versus how much time has passed, that's the horizontal one. Every line, every curve on here is a little story.
And you can actually read this story just by looking at the shape of the line. If you see a straight, sloped line, that means the object is moving at a nice, steady speed. A totally flat, horizontal line? Well, that means time is ticking by, but the object's not going anywhere, it's just sitting still. If the line starts to curve up, oh, it's speeding up. And if it slopes back down, that means it's on its way back to where it started.
And here is the most important rule for these graphs. The steepness of that line, what mathematicians call the slope, tells you the speed. A general slope means you're going slow. A really steep line means you're moving fast. It's a super simple visual way to see speed.
Now there's another kind of graph physicists use a lot, a velocity time graph. It looks a little different. Here, a flat horizontal line actually means you're moving at a constant speed. And here's a really cool trick. The total distance the object traveled is just the area of the shape right underneath that line. It's another awesome tool to have in your back pocket. So we've talked about being still, and we've talked about moving at a steady speed. But, you know, the world is way more interesting than that. We speed up, we slow down, we turn corners, and all of that change brings us to one of the biggest ideas in all of physics, acceleration. All right, another little brain teaser for you. Imagine you're in a car, and the speedometer is locked, glued at exactly 60 miles per hour. The speed is not changing one bit.
So my question is, can that car be accelerating? Your first instinct is probably to say, no way. But physics has a little surprise for you.
Believe it or not, the answer is a huge yes. If that car is going around a corner, even at a perfectly steady 60 miles per hour, it is absolutely 100% accelerating. And that little fact opens up what acceleration really means.
You see, acceleration isn't just about slamming on the gas pedal. Remember how we said velocity is a vector? It has both speed and direction. Well, that means any change in velocity is an acceleration. So yeah, speeding up, that's acceleration. Slamming on the brakes and slowing down, that's also a type of acceleration, just a negative one. And here's the kicker. Just changing your direction, like a car turning, or a horse on a merry-go-round, or even the tip of a blade on a ceiling fan, that is also acceleration because your velocity's direction is constantly changing.
Now, physicists figured out the beautiful math behind all this. It came up with 3 powerful formulas called the equations of motion. These are basically the cheat codes that connect speed, distance, and constant acceleration. With these, you can predict exactly where something's going to be and how fast it'll be going. They're incredibly powerful.
All right, we have covered a lot of ground. We've talked distance, displacement, and acceleration. We now have all the tools we need to go all the way back to the beginning and finally solve that mystery of the person on the bus. This quote right here just nails it. An object can be totally still compared to one thing and flying by compared to something else, all at the same time. The conclusion is just inescapable. Things like rest and motion aren't fixed. It all depends on your point of view.
And the official physics name for that point of view is a frame of reference. So back on the bus, your frame of reference was the bus itself. In that frame, you were still. But for the person on the sidewalk, their frame of reference was the earth. And in their frame, you were moving. And the most mind-bending part, you were both right.
And to get just a little deeper, physicists split these frames into 2 kinds. An inertial frame is a point of view that isn't accelerating, it's either still or just cruising along at a constant speed. A non-inertial frame is one that's accelerating. Think about being in that car turning a corner or on that merry-go-round. The laws of physics can feel a little different depending on which frame you're in. So it turns out, you, right now, feeling perfectly still, you're actually on a planet that's spinning, and that planet is flying through space around a star at thousands of miles an hour. Motion and stillness are really just 2 sides of the same coin. It's all about your perspective. So the next time you think you're not moving, just ask yourself that one simple, powerful question. Relative to what?